Oh, there we go. Let's go live. In 5, 4, 3, 2, 1. Okay. So let's see if we've got anybody watching. One concurrent viewer. But you know what? The show can go on. So what we'll do is we'll just go ahead and get started.
What? One viewer?
Yeah, but more will join. And we are recording, so more people will watch this presentation.
Just on YouTube?
All right, so everybody, I am going to introduce Austin Sabatino and Tom Hagen. They are members of the McMath Hulbert Astronomical Society, newest members of the
recording this, right?
Astronomy of the Great Lakes Association of Astronomy Clubs. And we also have Oakland Astronomy Club of Rochester, Michigan. So as one of you, both of these societies are represented. And now Tom is going to get started and talk to you about radio astronomy. Tom, take it away.
Tom?
Well, thank you. Let's get everybody into the picture here.
Sure.
Are we shooting?
Yes.
Yeah, okay.
So,
yeah, I'm Tom Hagen, and this is Marty Kuntz over here and Austin Sabatino. We're going to do a little live presentation from the McMath Hulbert Solar Observatory in Lake Angeles, Michigan. It's a beautiful night here in Lake Angeles. Temperature about 70, clear skies. But of course, that's not a big deal because we do radio astronomy. Thank you for attending our presentation this evening. We hope you'll enjoy learning a little bit more about amateur radio astronomy. McMath Hulbert Observatory is a classic solar observatory. It did groundbreaking work over its active life from 1930 to 1979. Behind me here, we have a picture that was taken probably about 60 or 70 years ago. So this is what it looked like in its operational stage. Today, the trees have grown up quite a bit, and we do have a bit of a problem with trees, and we need to do some maintenance too. Our mission here as the McMath Hulbert Astronomical Society is to promote and preserve the observatory. Behind me is our homemade radio telescope that operates in the wavelength range of 21 centimeters, or a frequency of about 1.42 gigahertz, or 1420 megahertz. This is a special frequency because it's one of the radio frequency resonances of neutral atomic hydrogen that's found in our Milky Way galaxy in great abundance. As you know, the Milky Way is our home galaxy. When we talk about neutral atomic hydrogen, we're talking about a single hydrogen atom that has a proton and an electron together. It's not an ionized hydrogen atom. There are emissions from ionized hydrogen, but we're not talking about that tonight. There's also optical emissions too from ionized hydrogen. The radio telescope here is what's called a horn form. Does not make an image like you would see with an optical telescope. It's really just a sensor that detects the strength of the received radio signal. It operates kind of like a light meter, only it detects brightness in the radio frequency spectrum and not the optical range. The output is a graphical display on a laptop PC that operates the software-defined receiver. So before we move ahead, I'd like to show you an 11-minute video that explains how we built the telescope and how we operate it. Okay, Austin? Hi, I'm Tom Hagen. I'm a member of the McMath Hulbert Astronomical Society, and we meet here at the historic McMath Hulbert Solar Observatory in Lake Angeles, Michigan. But before we continue, here's an explanation of how neutral hydrogen, H1, generates the 21 centimeter emission line. The proton and electron have the quantum property of spin, which is related to angular momentum. These spins can have one of two directions, up or down. The atom is in the high energy state when the two spins are aligned. It is in the low energy state when the spins are aligned in opposite directions. When the atom is in the high energy state and the electron flips from up to down, a 21 centimeter wavelength photon is emitted, and we can detect this radiation on Earth from the countless hydrogen atoms in the volume of the Milky Way. And today we're going to show you our homemade radio telescope that we use to detect the emissions of the hydrogen gas in the Milky Way galaxy. That's our home galaxy. Okay, so here is the radio telescope itself. We built this ourselves right here at McMath Hulbert in our shop. And this is an antenna called a horn antenna.
Well, I guess if we
It's basically a funnel for radio frequency energy. We're trying to detect radio frequency energy that is generated by the hydrogen atoms in our Milky Way galaxy. That's our home galaxy. So when I point this up to the sky, the energy just falls in here, and we can pick it up down at the end down there, and we can detect the signal strength that way. So when we point it up, we can detect whether or not we're seeing hydrogen in the sky from the Milky Way. So if you come in a bit closer here, this is all these materials are available at Home Depot. That's where we got them. The uprights here are 3/4 inch birch plywood. The base is made out of some aspenite that we had as scrap here. It's about 40 inches in diameter. On the top we have another plate that sits on the ground, circular plate. That plate has casters mounted on it so that we can turn it back and forth in azimuth. The altitude axis is made up of these toilet flanges, PVC toilet flanges from Home Depot. More 3/4 inch birch plywood. The horn itself is made out of 1 inch aluminum angle screwed together. The metal here is 26 gauge sheet metal. Again, all this is available at Home Depot. The design of the horn itself comes from an organization that's been searching for extraterrestrial intelligence, extraterrestrial radio signals. I took their design, I modified it a little bit. I added this tailpiece back here, which is where the antenna itself is, so that I have a better antenna pattern, a better pattern as it looks up into the sky. Again, to reiterate, this is basically, it's just a sensor. Even though it's called a telescope, we don't make pictures with it. Looking inside the horn, you can see how it's assembled with screws, and it's held together basically by this aluminum angle, this 1 inch aluminum angle material. On the corners, we mitered the joints, and we have double angled here all the way around, so this makes the front end really stiff. If you didn't do it that way, this thing would tend to be a little bit floppy. The pieces were cut with a aviation snips, so it is kind of a rough edge there, but I was careful when I built it to turn the rough edges inside so that you don't have the problem. And then down at the end here, this is where the signal is detected, and we have this little probe here that is tuned to the wavelength of the frequency that we are trying to receive. That wavelength is 21 centimeters. That is a known emission line of hydrogen atoms. Here is where the active element comes out of the tailpiece here, and it hooks to this piece of coaxial cable, and it comes out here and goes up here to this preamplifier, which is a little amplifier board inside this metal box here. This board amplifies the signal by about 1,000 times. The signal comes in here and it goes out here, and then we hook our radio detector to this output coax here. This other wire here supplies power to power the amplifier. As it is, we have about 12 volts DC input coming in here. So basically, this little device here is the actual receiver that we hook our output signal to from the antenna. This is called a software-defined radio dongle. This is a device that plugs into the USB port of a personal computer. For example, we could plug it in here, and we can use software to communicate with it and set it up to receive the signal that we want, that we're looking for. But I have decided that I don't want to plug it in that way. I want the device to be very close to the antenna, because that improves the noise performance of the system when I do that way. So I just screw the coax in just like this, and then I bring a long USB cable from the device, and then I plug it in to my laptop over here. Next thing I need is I need to connect power to the preamp through this fairly long wire. Just plug it in right here like that. So there, that's the those are the connections at the horn itself. Okay, so now we have this set up, powered up, assembled, and in operation. We started the software on the, this is a Linux computer running Ubuntu, and we're running an application called GNU Radio that communicates with our receiver over here at the horn itself. The display on the laptop here, it's a little hard to see here, but we'll have some screenshots of it for you to look at. This is the signal, and we're on the horizontal axis, we're displaying frequency, and then on the vertical axis, this is relative strength. So if you can see this, right here we have a little bit of a bump here, and that is the signature of the hydrogen atoms in space. Now, to make it a little bit easier to see, we can do signal averaging, what's called averaging, and we're averaging 40-some signals over time here. And as you can see, this allows our signal to show up a lot better. Okay, in this slide, we're showing the output that the operator sees on the laptop. This is the output from the radio telescope. The dark green line here is the actual signal from the receiver. We have frequency scaled along the bottom, and then on the y-axis we're showing relative power. So this is a fairly noisy signal, and what we have here is the signature of hydrogen. Basically, it shows up as a bump along here. Now, it's not very clear here because the signal is pretty noisy, but you can see a little bit of a rise here. Now here in this shot, we're using the averaging function of the software, and the receive signal of the H1 line, the hydrogen line, is much more prominent. So this is how we use the radio telescope to detect hydrogen emissions from the Milky Way galaxy. Thank you for watching this video. For more information on how to build your own radio telescope, contact us at mcmathhulbert.org. Also, you may also want to take a look at the Oakland Astronomy Club website, oaklandastronomy.org.
All right, and we're back.
Okay, we're back. I hope you found the video informative. I don't know if I'd hope for entertaining or not. Yuck, yuck. Let's take a look now, and we're going to see how the telescope actually operates to detect hydrogen in our galaxy. Excuse me for just a second here. What we're going to do now is show the operation of the telescope a little bit. We want to display the actual signal on our laptop here that's controlling the computer. So Austin, if you could switch it over to this computer.
So what I'm doing now is I'm making sure that video is unmuted so you can start it. You should be able to start it on your laptop now. So you may have to click.
We're waiting. This one's a little bit slow.
Yes, Adrian, it's the Linux laptop, so it's.
Oh, okay. It's taking a while to boot. Yeah. So not a problem. We're let's see where we're at time, 8:37. Yeah, we've got some time. And I'm familiar with the travails of booting Linux. But I know the machine, once it boots, it does its job. So those that are on the presentation, I see that there are 17 of you. If you have any questions, feel free
What
to
we can
ask.
do is we can
Yeah, let it take some time. Because I've got some questions for you. I'll throw you a curveball while you're trying to fix that. I wrote down a question about radio astronomy and supernova events. Have you ever caught something like that from a radio telescope? And if so, what does it look like?
Sorry, Adrian. Could you repeat the question?
The question was about a supernova event, and have you ever caught one of those on a radio telescope?
Tom, did you catch that?
Yeah,
I'm sorry.
It's have you ever caught a supernova event, or what does a supernova event look like from a radio telescope?
I've never seen one. I don't even know if there's been very many observations by professional observatories because it is so fast and it's so rare. Radio astronomers do look for transient events called fast radio bursts. And that's kind of an active area right now in radio astronomy. In astronomy in general, transient events are getting to be more and more emphasized. So maybe what we can do, Austin, could we switch back to the camera and place the camera on this display here?
So the issue is it's just not seeming to want to screen share with the Linux laptop. So that's really our main catch up here.
Oh, you know what? I think I have to assign your Linux laptop so that it can screen share.
Okay, it would
So
be the
which
one labeled
is it?
Tom there.
Let me do this. All right, go ahead and try it.
Let's see.
Taking questions from the chat room.
Yeah.
And let me make sure.
Actually, close that one.
Close this one.
Okay, so all three of your screens should be able to share.
There
There
we
you
go.
Okay, can
I
we
think
see
we
it
got
now?
it.
There
Yep.
we are.
There you go. All right, carry on.
All right. So what we're looking at here is the actual display on the laptop that's running the radio telescope, the software-defined radio that we're using. And what you can see here, this is actually the hydrogen signature from the galaxy itself. Now, it's, as you can see, it's kind of a noisy signal. It's a little bit hard to see. The software program we're running allows us to do averaging on the signal. So this averaging really cleans up the noise a lot on this. So if I select averaging, you can see now we have a kind of a nice little bump here at approximately 1420 something megahertz. This is basically the output of the whole telescope. So maybe, you know, it may not be as exciting as looking at the rings of Saturn, but you know, as amateur radio astronomers, we think that's kind of fun. So now if we move the horn away from the galaxy, Marty will assist me here. And we reset our averaging and start averaging again. You can see that we actually lose the signal. It may be still there, but it's quite a bit lower. And you notice we probably are receiving it here. This is not away from the galaxy. So you can see the frequency has shifted a little bit. The frequency shift is kind of important in that it's caused by Doppler shift, which is the shift in frequency that's caused by the relative velocity, radio velocity between us and the source. If we had a clear sky here, right now we're looking up at Cygnus. Galaxy, as you may recall, runs right through Cygnus. So Cygnus is straight up right now. That's where we're looking when we see the strong signal. So Marty, let's move back to Cygnus.
And where would you like to move to?
Okay, right now,
Back to the Milky Way.
yeah, back to the Milky Way, please.
Okay.
Now, if we had a clear view of Cassiopeia, which we don't because of the trees here, we could actually see two spikes. These spikes represent areas of the galaxy that have the same relative velocity to Earth. So that tells us when we see a spike at one Doppler shift, we're looking at one part of the galaxy that is an intact piece. If we see two, then we're looking at two separate pieces. Now, this is interpreted by radio astronomers as two different arms of our galaxy. Our galaxy, of course, has multiple arms. But a little bit about Doppler shift, you may understand that it's the, you can hear it in the audio range. A good example, typical example is the sound of a police car siren that is higher than normal when it's approaching, and then as the car passes, the siren drops in frequency. That's Doppler shift. So we can see the Doppler shift here. We can interpret the amplitude as the rough distance to the source, and the Doppler shift tells us the what we're actually looking at. That may be a single defined object in the galaxy. Again, that's an arm of the Milky Way as interpreted. This is how the arms of the galaxy were mapped out originally in the 1950s by radio astronomers. Now we've got another mode of operation, and that is called thermal emission. Now, if we go back to off the galaxy, let's go tip it back that way a little bit. We see that we're getting a noisy signal. And what we have here, some of this noise is caused by the radio receiver itself. Some of it's coming from the universe. And this is caused by a process, again, called thermal emission or black body radiation. Now, black body radiation is electromagnetic radiation from a solid, liquid, or gas under high pressure that has a temperature above absolute zero. Absolute zero is the lowest possible temperature that matter can achieve. In other words, it's there's no thermal energy at all in the matter at this temperature. The fundamental particles of nature have minimum vibrational motion. So this is another way to study the universe. Thermal emission has a very broad bandwidth. And if we could show the black body diagram.
Yep. Adrian, I will share that on my screen here on Austin's laptop. You want to stop that screen share on there?
Now, I hope everybody sees the black body diagram. It has a characteristic shape in that it, this is wavelength along the bottom here. We're looking at fairly short wavelengths. And we have three black bodies represented here, one at 5,000 Kelvin. That happens to be the temperature of the sun. And this black body radiation characteristic has a peak in the visual range. So that's where the sun is brightest, in the visual range. If it's an object at 4,000 Kelvin, has a peak at a longer wavelength at lower frequency, 3,000 Kelvin, even lower still. So our bodies, for example, are at 310 Kelvin. We can go back to the display here on the other one. So, for example, if Marty turns it back up to what's called cold sky, he can actually put his arm across the telescope and you can see the signal strength go up. This is radiation from the human body at 21 centimeters. So the equipment here is sensitive enough to pick that up. And we'll get an even higher energy if we point it to the ground. Even though the ground is cooler than Marty's arm, there's more area here, and so we're detecting more energy.
One moment. So we want to get the Tom's laptop back on the screen there. let's screen share that so we can show. Do you want to
Yeah,
navigate this guy here?
Oh.
Should get you.
sorry. Oh, no. Tom, up here again.
I
Oh,
got it.
sorry.
All right.
Okay, sorry. Okay, now we're pointing the horn at the ground, and you can, as you can see, we're getting a very high level of radiation. That's the radiation from the ground itself at about 290 degrees Kelvin tonight. Again, let's turn it back up, point it straight up at what's called cold sky.
Clear sky.
Cold sky, yeah.
Gonna go this way.
Yeah, okay. See the signal drop back down toward the cold calibration there. Marty sticks his arm in the horn, and you can see the level come up. So anyway, this just goes to illustrate that a radio telescope can be used as a thermometer that detects the temperature of objects in the sky. Radio astronomers typically calibrate or characterize the brightness of radio objects in terms of temperature or degrees Kelvin. So I guess that's about all we have tonight. I think we're running a little short on time, it looks like. So
Yeah, that's actually
I
perfect.
guess that's about it. Hope you enjoy the presentation. Are there any questions?
So right now we don't have any from chat. I'll go ahead and share because we do have some watching, and you have I think 15 viewers that are still watching, and I want to go ahead and quickly get a couple of the questions that others may have. One good one is, how much did the full setup that you're using cost?
The SDR, software-defined radio dongle, was about $100. It's an Air Spy. It's a brand commonly used in this business. The preamp, that was about, I built that from a kit. That was about $100. We have maybe $100 in the materials for the horn, the sheet metal.
Okay, we actually have a question now from a viewer. Ken Lord asks, is the large peak at 1.422 real or an artifact of the sensor? Hopefully you all heard that question.
Sorry, Adrian. One moment.
Okay.
Adrian, can you shift the view back to the main camera there?
Sure. Let's see what actually it is. I'll stop my video and then you all should, because you're still sharing your screen right now.
Oh, yep. If you want to hit that stop screen share at the top there.
There we go.
So anyway, thanks for watching, everybody.
Yep. So there's a couple more questions actually. So
sorry. I
yeah,
can't hear
so
you.
we got two questions.
Okay, go ahead.
Yep, the first from Ken Lord, is the large peak at 1.422 real or an artifact of the sensor?
That is a real signal.
Okay. And then Jim,
Or was that
elaborate.
Sorry, was that a narrowband spike?
I think it was.
Okay, that probably was an ambient RFI signal then.
All right. And then Jim Shedlowski has a question. How much do the trees affect the signal level?
Basically, the trees block the signal by virtue of the fact that they're radiating and they're overpowering the signal we're trying to see.
Okay. And then I had a question about if radio astronomy works when it's cloudy weather. I think you may have just answered it because it's probably similar to the trees. But can you do radio astronomy in non-clear weather, we'll say?
Yeah, if it's not raining or snowing, you know, the heavy wet snow typically wipes us out. But if it's cloud cover's thin enough, we can get through it.
Okay. Excellent.
Tonight is beautiful
So
clear
we'll
night.
put
though.
it out to the folks. If there's any other questions, we have time for one more question before we can go. If not, Tom and Austin and the rest, I forget your other assistant. Marty. We thank you for this presentation, a very informative presentation. And I think a very good presentation. You did have some viewers watching, and so they were, yep, Lynn Ertel says, this was fascinating. Thank you. So we thank you for this presentation, and we appreciate it. We appreciate you all doing it from the shadow of the McMath Hulbert Observatory, which for those of you that are watching, that's where they're at. They're out in the shadow of this building that they had on the screen. So thank you for the presentation. I think it went well. And we'll go ahead and stop the live stream. Thank you all for joining on the on YouTube, and enjoy the rest of virtual astronomy at the beach.
Thank you, Adrian.
Bye.
You're welcome. See you all.